Okay, well, there's a old geological aphorism that says that anything that did happen can happen. And so in that spirit, I'd like to show you kind of some examples of an interesting phenomenon that's been recognized for about 40 years now, which is that sometimes, and for reasons that we do not really understand, large, by that I mean more or less magnitude 7, continental earthquakes can have aftershock sequences that go on for decades and perhaps even hundreds of years. And so I'd like to show you some examples of this phenomenon. As I say, we do not yet understand it. And then I want to show you some of the possible things that one needs to think about this phenomenon when you think about assessing earthquakes in continental interiors. This is the first publication on the topic I have encountered. This work by Ryle, and he was looking at the, do I have a marker?
A pointer?
Pointer, yeah. Oh, okay, yeah. He was looking at aftershocks in the central Nevada seismic zone, and what he noticed, this was the 70s, that he could easily see the aftershock zone of the 1954 earthquake, and the 1932 earthquake, and the 1915 earthquake, and as he went further back, it was harder and harder to see this. So he made this graph here, and he said, look, it looks like aftershocks in Nevada go on for about 100 years. And that is sort of where we are. In other words, we can very easily find examples of this phenomenon, and I will show you a bunch of them. At the same time, it's surprising, they're very easily noticeable, they're hard to quantify, and that we don't really understand how this works yet. There's a nice picture here by Tom Parsons that kind of illustrates the issue. When you deal with a plate boundary earthquakes, plate boundaries are fairly active, so you get a main shock, you get a decay of aftershocks. Within about a decade, you come back to your pre-earthquake rate, and you can easily pick out and identify that number. When you're dealing with continental aftershocks that are long, it'll take you hundreds of years to get down, and that's more or less, you're running into the lengths of your catalog, and even before then you're running into incompleteness and non-uniformity in your catalog. So it's really hard, it's easy to identify this, but it's really, really hard to quantify this phenomenon. One can use various models, but of course what you're then doing is you're taking models that were constructed and tuned to describe very short duration aftershock sequences, and then saying, oh, I don't know, these probably work for things that go on for hundreds of years, whereas you know perfectly well that they can't work very well for hundreds of years because otherwise the earthquakes would behave the same way, and they don't. So this, in a sense, is a summary of the problem, and I'll just try to illustrate some examples. This matters quite a bit for earthquake hazards in continental regions. This is the aftershock zone of the 1976 Tangshan earthquake that destroyed the city. And the city's been rebuilt, but there's still a lot of concern because the earthquakes continue there. So the obvious question for the Chinese authorities is whether this is telling us that that a big earthquake is on the way, or whether these are simply aftershocks. It's an analysis here by Mian Liu and his co-authors, and what they've shown is that you can make a pretty good case that this is a decaying aftershock sequence. We're, 35 years out into this sequence. We're still not down to the pre-earthquake level. So it looks pretty likely that these are continuing aftershocks, and these will go on for decades to come. You can see the same sort of thing in the Haicheng earthquake that was the year before. Same sort of decay here, still well above the pre-earthquake level. Other analysis of this, John Ebel has thought about these questions quite a lot. And one of the things, this is a map that he's made. This is California seismicity in 2004 abouts. And you'll notice that the 1952 Kern County earthquake is quite visible in the aftershock zone. Now that is not part of the plate boundary events, the high strain, the high deformation rates. This is a small, this is a slow deforming white wolf fault that's moving much more slowly than San Andreas rate. Lots of other examples. The people who have been interested in the Hebgen Lake earthquake, also about the 1950s, have noted that the aftershocks of that area continues to be quite active today. We've been looking at the locations of the two largest earthquakes in eastern North America, which is 1929 Grand Banks and 1933 Baffin Bay. They're both kind of remote places, but you can see those areas remain active today. And again, given the network problems, it's hard to see much in the way of structure, but you definitely see that these are continuing to be active and they're continuing to decline. You can even go further back in time. This is Mongolia. All the red events are post-1964. And you can easily see the 1857 earthquake, 1931 earthquake, 1905 earthquake. 1957. Thank you. Yeah, thank you. Yeah. This is Charlevoix, the St. Lawrence Valley, big earthquake there in 1663, so much smaller one, 1925. This zone here really stands out from the rest of the St. Lawrence Valley, and so a number of people have said, probably what we are seeing is aftershocks today of Charlevoix. So if you put all this together, you can sort of see that there seems to be a general pattern here. The pattern is what you'd predict from paper spawn rate state friction by Dietrich, which basically says that aftershock duration scale is 1 over the loading rate. And you sort of see that. The plate boundaries deform at about tens of millimeters a year. Aftershocks seem to go on for about 10 years. When you get to the plate boundary zones, you pretty much have to put one-sided constraints on them, as in Tangshan is still going on, so it's longer than 45 years. Those are deforming at about 1 millimeter a year. When you get to plate interiors, deforming at well under 1 millimeter a year, you're probably dealing with hundreds of years. Basically what's happening is conceptually simple and enormously complicated in detail. You can make many other models than the rate state one that will all give you the same answer. Plate boundary faults are quickly reloaded by steady plate motion. So 10 years after a plate boundary earthquake, the effects of the earthquake are swamped by the reloading. Within the continental interior, 200 years after the New Madrid earthquakes, the biggest stress signal in there is still the New Madrid earthquakes because the reloading is so incredibly slow. So not surprisingly, the stress adjustments continue for many hundreds of years. What this implies, and this is something that Ebel and others pointed out first, that when you see seismicity on an earthquake map within a continent, a lot of these are likely to be aftershocks rather than telling you the location of future events. Then this is part of a general phenomenon that continental earthquakes behave this way. Basically, everything is coming from this super slow loading. So you get a lot of time variability. You get transfers of seismicity from one to another, aftershocks for a long time. And so what does a seismicity map actually tell us? That's what I'd like to finish up with this New Madrid example. We would expect from stress transfer that the stresses in the Wabash Valley and in northern Arkansas would be increasing as a result of the 1811, 1812 earthquakes. The Wabash Valley is an obvious target because there's something about magnitude 7 implied from the paleoliquefaction about 6,000 years ago. So this was presumably the New Madrid zone of the time. So how do we look for this? Well, one of them was to simply look for low B values because these are supposed to show high stressing rates. We've looked at that. And this is the B-value curve for New Madrid. This is for Wabash. At first sight, you think you see it because Wabash is lower B-value than New Madrid. But if you take the following experiment, if you simply take all of the central US and we take out both New Madrid and Wabash, the green is what remains, and it basically looks like Wabash. So our interpretation is Wabash is the usual state of affairs, and New Madrid has been pumped up by the aftershocks. There's a lot of reasons to think that makes sense. One thing to realize is that although we tend to think about Bs1 being the norm, in fact, low B values are common in intraplate areas. 0.8, 0.7, something like that is seen both globally and in lots of intraplate areas. So what are the reasons that makes this make sense? Well, the simplest is that for many, many years, people, this is one by Suzaf, have been mapping the 1811 and 1812 ruptures by taking the more recent earthquakes and saying, okay, that's how I define the rupture. So once you do that, you are by definition saying they're aftershocks. Otherwise, this procedure would not be a useful procedure. And most everybody that's looked at New Madrid has more or less come up with the same sort of argument. Data, you sort of see this, it's not as convincing in the decay sequence. It's not very good from historic data. You definitely see a pattern, and various people have commented on this, that the larger of the post-1811-12 events are always at the tips of this aftershock zone and presumably the tips of the rupture. So the whole thing sort of hangs together. You can't prove it. What's the implication for hazards? It says that your aftershocks are the hazard. That's what's going on today. We know the area is not being loaded. This is the most recent GPS results presented yesterday by Tim Craig and Eric Calais. The GPS data have now stabilized. They're quite good. We know that the deformation rate is less than 0.2 of a millimeter a year. So in other words, at this rate in steady state, it would take you 10,000 years to build up strain for a future large earthquake. So right now, most of the hazard we're seeing is actually just these aftershocks. Those are more or less a 6 every 200 years, 5 every 20 years, and that decay rate is slow enough that you can more or less regard this as steady state. It's a steady state on a human time scale, like 50. So this is one of the reasons why we've said that we think a better estimate of the seismic hazard is not the very high hazard in the National Seismic Hazard Maps that assume a magnitude 7 or 8 or something are incipient, but rather something that says we'll expect to see the current level of seismicity continue more or less indefinitely, preventing a modest but not huge seismic hazard. So conclusions. Large continental earthquakes sometimes, and it does not appear to be all of them, and we don't know why this is, have aftershock sequences much longer than at plate boundaries. It's consistent with what we expect from rate state friction due to the low slow loading rate or other models. The concentrations of small intraplate seismicity may reflect large past earthquakes, ghost earthquakes that we don't know about. The seismic hazard in intraplate seismic zones, in some of them, is probably dominated by these long-duration aftershocks. And here's one, this is an empiricism that we have not studied in detail, but I think is probably true, that fortunately the declustering algorithms, like all aftershock algorithms, are tuned to the short 10-year decay rates. That is very fortunate. Because if you were to decluster your catalog and your algorithm was really good, it would remove all of these events that are in fact aftershocks, and it would remove what is in fact your seismic hazard. So fortunately, these things do not remove these things because your aftershocks are not something you want to remove to estimate the hazard. In these cases, the aftershocks are the hazard. Thank you.
Questions for Seth? Yes, Alyana.
I have a comment. I am very encouraged by the graph you have shown, very long aftershock. We have not yet seen the next one, meaning you said that it will take hundreds and thousands of years for not one. So I think this is a question about the model of recurrence. When is this recurrence? Because your graph did also any other, just a big one and decay. So what is the next one?
Well, the next, we would expect the sixes.
You have to repeat the question.
Oh, sorry. What would we say about recurrences? Well, this argument does not directly tell us about the recurrence of an 1811, 1812 style earthquake. It tells us that we should expect a 6, if you believe that this is more or less steady state, about once every 200 years, a 5 about every 20 years. Those seem to be fairly robust numbers. So what we've done for that earthquake hazard map I did is we just ran that out to 500 years and said, oh, I don't know, you might get a 6.5 or something in there. It doesn't directly give us information about when you would expect to have another 1811-12 style earthquake, unless you believe that that can be described by the same population. Okay? In that case, they would be, roughly every 2,000 years, and that's kind of an underestimate. That's an overestimate because we know the last couple have been about every 500 years. Yeah.
Thank you, Seth.